To do something a little different today. We were talking about, just at the end of the renormalization group part, I was talking about we saw the double well emerging, and that's a signal of a phase transition. And in fact, the most detailed description we have of phase transition is through the renormalization group, but it gets ferociously complicated, especially if you want to prove things rigorously, if you're trying to study systems with what I'll call continuous symmetry, which is what I want to talk about today. So I'm going to describe today that more or less the only nice method we have to prove existence of phase transitions. It's quite old, goes back to a paper of Froelich, Simon, and Spencer. And in certain sense, we haven't made much progress since then beyond this method, which is rather sad. And so I think it shows you where the frontier is a little bit to go through this method. So you remember that at the beginning of these lectures, I asked you whether the bed spring is loose or floppy at the center, right? I don't know whether anybody came up with an answer to that, but let's look at it now. So we're looking at the massless Gaussian. So this is actually an example. So it's e to the minus grad phi d lambda phi, 1 over the normalization. And we're going to put Dirichlet boundary conditions. So we'll set phi equal to 0 outside lambda. And this is the model that I suggested you can think of as a bed spring. So the frame of the bed sets the field phi equal to 0. And you can think of the phi as a displacement orthogonal to the blackboard of the bed springs in the middle here. Etc. And the question is, if I make this bed spring bigger and bigger, and I look at, and if I'm lying at the center of it, am I going to oscillate a lot, or is it still going to remain relatively rigid as the boundary is removed to infinity? So one way to decide this question is to simply take the point at the middle, which I'll call the origin, and to calculate the variance of the field at that point. So let's call this measure d mu sub lambda. And let's calculate d mu sub lambda phi naught squared, which is the variance, because the measure is even under the symmetry phi goes to minus phi. So certainly the mean of this measure is 0 if I set phi equal to 0 outside. And so that is the variance, just to calculate the square. And we can do that by Wick's theorem. Well, we know we know how to calculate the variance. We simply invert the operator, which is the Laplacian here. So we have to calculate 1 over minus Laplacian, and we have to take the 0, 0 matrix element. And this is the Laplacian with a subscript lambda on it, because you see I've got this boundary condition phi equals 0, which is defines this matrix here from this bilinear form. So it remembers that the Laplacian knows about the lambda. Now, in fact, as you make the lambda bigger, this increases. So the question is, does it increase a lot or does it increase a little? And to see that it increases, by the way, there's more than one way to do it, but in Tom Spencer's lectures, he mentioned that you can write this as a sum over walks that go from the origin back to the origin. And the effect of the boundary condition is to keep the walks inside the lambda. So if you make the lambda bigger, you're actually summing over more walks, and that's a simple way to see that it's getting bigger. So I'll just put that remark down. Now, if you just accept then that it's increasing, then we can get an upper bound on this object by calculating what it is in the infinite volume limit. And there we have translation invariance, presumably. And if we have translation invariance, we can use the Fourier transform to diagonalize the Laplacian. And again, in Tom's lectures, he showed you what that is. So basically, I'm arguing that this is going to be less than, and I'm going to write down the Fourier transform for this inverse, and that looks like this. dk1 over 2 pi dot 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 dk sub d in d dimensions over 2 pi. And each of these integrals, as you remember, goes from minus pi to pi over a Brillouin zone, as it's called. And the eigenvalues of the Laplacian you find by letting them act on plane waves like Tom did. And you might remember that he had some expression like the sum j equals 1 to d of 1 minus cosine k sub j. And the j is labeling the components of the momentum, so it's the k1 to kd here. The precise form of this thing never matters in these calculations. What always matters is what happens when k is equal to 0 or near 0. And then you know that this thing here is behaving like 1 over k dot k squared. I mean k dot k. And so then we see that this number here is finite if the dimension d is bigger than 3. Because 1 upon k squared is integrable if you have more than 3 integrals to integrate. More than 2, sorry, more than 2, yes, greater or equal to 3, exactly. So, what is this telling you? It's telling you that this variance remains finite as the boundary is removed to infinity. Uniformly is bounded as the boundary goes to infinity. So, this model, this bed spring remains stiff in the center, relatively. In 3 dimensions or more, right. In 3 or more dimensions. So you have to have a 3-dimensional bed spring in order to be able to lie on it comfortably, I guess. Now, if you're in 2, well, let's stay with this 3-dimensional example just for a second to try to milk it for what it's worth. What does it tell you about? There's a symmetry here in this expression. If you just looked at this alone and you forgot about the boundary condition, phi equals 0, you would say, well, I can just change the phi's by adding the same constant to all of them, right? And the gradient wouldn't know that. So that's a kind of symmetry of this expression here. It's a symmetry under changing phi by a constant translation. And what we're seeing in this 3 or more dimensional case is that the symmetry is broken at the boundary because we set phi equal to 0. That's basically what tells the phi what to fluctuate around. I mean, in any finite volume, what you set the field equal to the boundary, which was 0 in this case, but could equally well be 23, that tells you what the mean of the field should be and what it will want to fluctuate around. And in 3 dimensions, it's going to remember that. The variance will remain finite. It'll always, in some well-defined sense, be fluctuating around the boundary condition, no matter how far away the boundary is. And that's a case of broken symmetry. Namely, the boundary, no matter how far away it is, breaks the symmetry of this object under translations. Even in the infinite volume limit, after it's been taken away totally, it still remembers it. So if you contrast that with the case of d equals 2 and 1, then I haven't proved it here because this is only an upper bound, but in fact, again, going back to the random walk interpretation, this is actually, as Tom said, a measure of whether random walk returns to itself finitely often or infinitely often in the dimension d. And in 1 and 2 dimensions, random walk returns to itself infinitely often, and this number really does diverge as you take lambda to infinity in 1 and 2 dimensions. So, yeah. Am I talking?
Inverse participation ratio? Shouldn't that then pi 0 to the power of 4?
No, no. I don't want to do phi 0 to the power of 4. I mean, one could. If you wanted to, you could calculate that as well, and you'd find again that it's finite or infinite. That would also be a measure of how much fluctuation is going around. It'd be a finer measure of fluctuations, but the variance is good enough for the argument I'm making. I just want to say we can test for the presence of symmetry breaking or not just by looking at whether this field fluctuates in a well-defined way around a mean.
The inverse participation ratio is something we look at when we study normalized wave functions.
Yeah.
The integral of psi squared is 1, then that is not an interesting thing to look at. We then better look at the integral of psi to the 4th, which has some information.
Yeah.
But there's no such normalization condition. David is just asking what is the variance of this field? How much, does it vary?
So how much does it oscillate in the middle, basically? How much does it fluctuate by? So, indeed, let's put this up a bit. In d equals 1 and 2, the variance d mu lambda phi naught squared goes up to infinity as lambda goes up to zd, and this can be interpreted as the field restoring symmetry under phi x goes to phi x plus constant, all x. That's under the so let me write this in a more clear way. What I'm trying to say is under that particular symmetry, restoring the symmetry. I'll write it that way. So the boundary condition breaks it. You take the boundary away. It is attempting, by fluctuating more and more, it's an interpretation of the fluctuation going to infinity, of the variance going to infinity. It's attempting to restore its symmetry under phi goes to phi plus constant. Now, unfortunately, if I wanted to use this as a main example, this wouldn't be very convincing because that's a non-compact symmetry because the translation is in R, is in the real line. And so actually, really what it happens is it just blows this field phi out of the water totally. The field phi, in a certain sense, doesn't exist as a good random variable in the limit where you take lambda to infinity. All that survives is differences of phi. You can, the difference phi at one point minus phi at another point, that remains a good random variable. But the phi itself loses its qualifications as a random variable. That's because of this symmetry. You can't normalize it, right? Precisely. It's trying to become Lebesgue measure, basically. The distribution of the field phi is trying to become Lebesgue measure, and you can't normalize that. Yes?
Well, does it make sense to rescale them phi according to some power?
Yes, you could if you wanted rescale it, but unfortunately what will happen if you do, the rescaling you'd have to make in order to bring the phi back down to Earth would kill the fluctuations, and you'd get a constant field. So the field phi in 2 dimensions doesn't really exist. And in 1 dimension, as I mentioned, phi can be interpreted actually as a random walk. And you know that you have to start the walk somewhere in order to normalize it. It's a similar problem. So that's a little example just to get you warmed up, and it's kind of amusing, I think, the bed spring business. But really what we want to do today is to see this symmetry breaking phenomenon in a much clearer way. And for that we want to talk about compact symmetries, where we can both see both sides of the situation when it's broken and when it's not. So today we'll consider models of this form. So they'll look like this. There'll be a product over points in lambda, and at each point you'll have a measure, and then there'll be the same grad phi in a product grad phi bilinear form, which looks very Gaussian. So what makes this model not Gaussian is this thing here, the d rho. So d rho, I'll just give you an example of, let's have 2 examples. Well, before we have examples, I want to emphasize now that I want to take this phi of x to be vector valued. Phi of x takes values in not the reals like I had up until now, but capital N is for some reason a traditional letter to use for the number of components of a field. R to the capital N. So I could of course put little vector signs over the phi's, but I want you to remember that they are in fact vectors now. And what does this grad phi dot grad phi business here mean? It means probably what you think it means, unlike tildes, which never mean what you think they mean. This is phi x minus phi y dot phi x minus phi y, where we sum over nearest neighbors x, y in the lattice. And the boundary condition that I want to use now is not the Dirichlet boundary condition anymore, but periodic boundary conditions. So we're thinking of the cases where lambdas are rectangular regions of the lattice ZD. And you identify that point there with that one there, and so on. Now, this row is then got to be a measure on a vector value. So this is a vector here, and so we want it to be rotationally invariant. So d rho should be ON invariant. I have to write ON instead of rotationally, but it really is rotations if, for example, the vector phi was taking values in R2 or R3. So a couple of examples just to show you what I have in mind here. They're actually the same example, but just changing n. The Ising model is capital N equals 1, and d rho of phi is delta of phi minus 1 plus delta of phi plus 1. So that's a sphere, think of this as a surface measure on a one-dimensional, on a sphere in 1 dimension, so it's just 2 points. This is Rn here. It's just 2 points. Rn is 1. So if we take this measure and stick it in here, then phi only has the option to be +1 or -1 when you do the integration. You get the Ising model. Actually, we would like the E-sink model with a temperature because we want to test its different phases by varying the temperature. The usual place to put the temperature would be here, but instead I'm going to scale it out of there and put it in the sphere. So I'm going to change this, if you'll allow me, to delta of phi minus root beta plus delta of phi plus root beta. And beta is inverse temperature. So a large sphere, a very large sphere, costs an awful lot when you flip from phi equals 1 to phi equals, from phi equals root beta to phi equals minus root beta, and that's how the temperature is being implemented here. Then a natural generalization is to just do the same thing as I have here in n bigger than 1. And then you'd have d rho of phi is surface measure or surface area on sphere inside Rn with radius, again, root beta. These are called the rotator models or the ON vector models. And sometimes they're called lattice nonlinear sigma models too. And so rotator is the case n equals 2. So the question then is, well, in this case, the E-sink model, we have a discrete symmetry. You can flip phi to minus phi. That's the only rotation, when I say ON invariant, in one dimension, O1, or is just the discrete symmetry. Phi goes to minus phi. Am I using that correctly? Is O1 that, or is O1 a circle?
That's O1.
What I did is O1.
O1 is Z2.
Z2, yes, right, good. Okay, so that's only a discrete symmetry, right? Lattice. So the E-sink model has a discrete up and down global symmetry. And then the question would be, will it remember that as the boundary is taken away or not? But in these cases, with this is called continuous symmetries here.
There's still a discrete aspect to it in the sense that ON has two connected components.
That's true,
Proper
yes.
rotations and the improper rotations.
That's true. I just want...
what would be of importance to you is the connected
right, the SON,
containing
yeah.
the identity.
Perhaps one should, the important symmetry I'm talking about is the S part, the connected part containing the identity, that's right. And this is a continuous symmetry, so the easiest, if you think about the case n equals 2 rotations, right? Now rotations are, again, it's sort of intuitively clear that rotations are going to be harder to remember as you take the boundary away, because if I fix all of the spins at the boundary to be pointing, say, in this direction, right? It can vary continuously away from that direction as you move inwards, whereas with the E-sink model, if I fix it to be this direction up, it has to make a really good decision to flip to the downward direction. That's the only option it has. So continuous symmetries are rather more difficult to break than discontinuous or discrete symmetries. That's an intuitive remark. And in fact, there is a theorem called the Mermin-Wagner theorem that says that continuous symmetries are not broken by these models in two dimensions. I'm going to be talking about 3 or more today. Mermin-Wagner. It's a very simple theorem to prove, by the way, this theorem. And continuous symmetry Now, I haven't defined what it means to say that the symmetry is broken, but I'm just making the theorem ahead of the careful definitions, but I think you can guess what it means. Continuous symmetry is not broken in dimension 2. So this is not the focus of the lecture today, it's just part of the general background to think about. Now,
and to be precise, the continuous symmetry had better be that of a compact.
Of a compact group, yes, thank you.
Not, I think the translation is also an example of compact geometry.
Yeah, but something has to be said. There are continuous symmetries that are definitely broken 2D. So you have to refine the statement in some way or another.
Yes. I was actually making the remark for this model. This is where it's simple to prove, is for these models, the rotational invariance is not broken in 2 dimensions. Let's put it this way. In these models. In these models being these models right here. That's what everything I'm saying today pretty much is associated with that. I'll tell you when I'm out of that context, if I get out of it. Now, so what I want to prove today is the following theorem. It's a theorem of Froelich, Simon, Spencer, from way back in the 70s. And it says that for d greater than 3, d greater than or equal to 3, for beta sufficiently large, which I'll write as for beta greater than 1, like that, there exists a constant c which depends on beta, which is greater than 0, such that the variance of 1 upon lambda sum x in lambda of phi of x is greater than c of beta, which, as we said, is greater than 0. And this is a bound which is uniform in lambda. So let's stare at that for a second and have a few remarks about what it means before I go on and prove it. This has a nice proof.
So
now,
don't we want to bound the variance from above?
No, I want to bound it from below. Because actually, the bound from below is what I want, because I want to prove, you see, think about ergodic theorems, right? I'll think about translations. These models, because of the boundary condition being periodic boundary conditions, and because these are homogeneous, there's the same d rho at every site, these models are translation invariant, where the translations I'm talking about now are not the ones I had before for the field phi, where I just moved them by a constant, but they're lattice translations. So if these models have infinite volume limits, this is telling you that they can't be ergodic under translations, because you see this thing is the average of the field over the whole lattice, lambda, over the whole torus, lambda. And that should be tending to a constant. If there was any kind of law of large numbers, that average should be tending to a constant as lambda is large. But what this is telling you is it's not becoming non-random. The variance is always bounded below. It's always a random variable. It's not becoming unrandom. So this is the reason, one of the reasons why I wanted to express it this way, is because it makes good contact with what you've been hearing in the other lectures. It's a failure of ergodicity. This is a failure of ergodicity. 1 over lambda sum. So the more correct, the right way to formulate this, exactly right way to say this, is construct an infinite volume limit theory of this model. I just didn't want to get into that, because I think we can see it at this level without doing that. But construct an infinite volume limit of this model, which means that you have to take, as we say, a weak limit of these measures here, of the measure associated with this thing. And as the volume is increased, And then look at 1 upon x, sum phi x, where little x is summed in x. And what we're saying is that this is not going to converge to the expected value. This is translation invariant, so you should be able to just take the expected value of any one point. It's not going to converge to that as x increases up to zd. Now, how can you interpret this? So the next statement is something I'm not going to prove, so I'm just going to prove this much here, but the next statement has more in it than that. But it means, so interpretation. An infinite volume limit has the structure a measure, a probability measure, on global direction. Times measure on fluctuations about global direction. So it's the interpretation is that this model in the infinite volume limit, you have this homogeneous field, phi, random field, but the probability distribution for that random field has the structure that there's an overall global direction which most of them want to point in. And there's a compact, just normalized surface measure on that global direction. And then the rest of the infinite volume measure can be considered as a measure on fluctuations about that as mean. So the whole model, you see, we didn't have a boundary condition in this periodic. We didn't have a boundary with a period, so it has to be said differently what broken symmetry means. We don't have a boundary, so we can't fix the phi equal to 0 on the boundary to fix this global direction. So this global direction actually remains in the structure of the infinite volume limit measure. And this is a non-ergodic measure. This part is ergodic in the sense that if you fix a global direction, for example, by putting on a boundary condition and taking it to infinity, then you'll only have this part here, and then this thing will converge because it will know what to converge to. This thing here actually has to converge in the case we have at the moment. All of these random variables themselves have to have mean 0, but they fluctuate like mad and they don't converge to 0 in this pointwise sense. Yes?
How don't having a limit is connected to non-ergodicity? You still can go wherever you want. The global direction can be any direction.
I think David is, let me try to put it.
Yeah.
He says, you want to construct an infinite volume limit. You try very hard. No matter how hard you try, you will not be able to define a limit where sort of the center of mass of the field is sort of uniformly distributed. No matter how you do it, your infinite volume limit will have to single out one direction.
If it's ergodic. If it's ergodic, yes. If the infinite volume limit is ergodic. So, you see, the ergodic theorem tells you, as we've seen, the ergodic theorem tells you that if the infinite volume limit were ergodic under translations, that would mean, by the ergodic theorem, that this thing converged pointwise. So, for each realization of the field phi, according to the infinite volume limit measure, this thing would converge to its average, which is 0. But it doesn't, because we can see that it fluctuates. The variance is bounded away. It doesn't converge. Yes?
Is the boundary condition important for this result?
Well, you have to have a boundary condition to select an ergodic component. So this is what we're saying is that the infinite volume measure is in fact an integral over other infinite volume measures which are ergodic. This is the probability distribution on the global direction. That global direction is set by a boundary condition if you have one. What we did with this periodic boundary condition was not to set any particular direction in the field.
You take zero boundary condition all day.
If you put zero boundary conditions, that would also not select any direction, right? Because so that would also lead to an infinite volume limit that had this structure.
And if I put in one point some fixed boundary condition,
If you fix it at one point on the boundary and fix it up, that's a hard question, what will happen then, okay? I mean, I went beyond what we can prove here. That's a question of classifying ergodic limits and what selects them, and that's not being done. So all I'm trying to say here with this statement here is that we have a situation which you can interpret as broken symmetry because the reason why the measure does not converge, the reason why this does not converge here is because we haven't selected in this model any direction for which is singled out and for which it knows what to converge to. It doesn't know what its mean should be. So you can just think of it as a model, you know, that the available spins are like this in the rotator. They are all absolutely equivalent in this setup here, where I didn't select any one of them by either boundary condition or in any other way. And the only thing this poor thing can do, if it's going to be in a broken symmetry phase, it wants to select one of these directions to have the majority pointing in, and it doesn't know how to select such a direction. So you end up with average over the possible directions it could select, and then an ergodic measure on the fluctuations around that particular direction. That's the structure that you expect this thing to have. Now,
so in the sense of doing an integral, we should do sort of the left factor as the last integral to do.
yes.
This is the outer variable, and then the internal variables are sort of the relative position, or the differences between the fields. That's
this
inner
one, right? Exactly. So this is a little bit tricky to get used to, but that's what I want to prove now. And it's nice that you're asking these questions because this is a hard thing to get a grip on. By the way, for the mathematicians here, what's happening is that this thing here is something that's in the sigma algebra at infinity, because this average cannot depend on the field at any one. Take any finite number of points. It's not a function of the field at any finite number of points. It depends on the. So there's a thing called the sigma algebra at infinity, if you know probability, and that's what this object is in. And what we're saying here is that the sigma algebra at infinity is non-trivial for this model in the broken phase. Now,
everybody understood what this non-convergent statement means, or should we?
Yeah, let me try and say it again. Okay, you see, notice there's no expectation here. That's the critical thing. There's no expectation in this statement. This is saying select at random from the infinite volume measure a whole configuration phi. Just pick one. Then
I'll do it according to the statistical measure.
yes, pick according to the statistical measure. So if you were thinking in terms of simulations, you would just pick one of these phis. You would simulate one. And then with the one you've simulated, take this average and try to find what the average spin is. And under normal circumstances, for example, if those were all independent, if they were all independent random variables, a strong law of large numbers would tell you that this thing converges to the expectation of any one of them. This is the expectation of one of them. They're all identical and independent, and then you would get zero because the expectation is zero, but it's not going to converge. Strong law of large numbers doesn't hold in this case. Now, I should add that much less subtle methods much less subtle than what I'm talking about for the rest of today, namely high temperature expansions, prove that infinite vol limit is ergodic if beta is small. So at high temperature, when beta is small, all of these spins start to feel relatively independent of each other, and then this thing does converge in the normal strong law of large numbers sense to its mean.
Question?
Yes?
Maybe, I think you are going to prove it, but can you qualitatively say now what's the role of that beta much larger than 1 in this non-ergodicity or failure of?
Well, it's making the model very stiff, right? If you have extremely huge spheres here, so think of this as a bunch of really huge spheres. At every point in the lattice, you have an enormous sphere which the field can take its values in, right? So it may be pointing in this direction, and then when you're at a neighboring point, it wants to point in almost exactly the same direction, because if it moves a little bit on this large sphere, that'll be a big displacement, and so it makes it very stiff to have large spheres. It's the same, it's clearer if you just scale it out of the sphere and put the beta there. If you put the beta there, if you take beta, suppose you put a beta here, it's absolutely equivalent, just scale it out by changing variables from phi to phi.
The further points are still contributing a lot to that.
Well, here, if you put the beta here, take beta to infinity, right? What's going to happen then? All the spins will point in exactly the same direction. They'll be forced to. And the only part of this infinite volume limit measure that survives will be this thing, the probability measure on the global direction, and there won't be any fluctuations about that global direction as beta goes to infinity. So that's the extreme low, there's absolute zero limit, where they all point in the same direction. There's no entropy in the system. So that's maybe that helps. Good. I think you got me to explain it relatively well there. Now,
We have moved past the Monday apathy.
yes, exactly. Very much nicer. Now let me show you the proofs of this. If I have time, you will see there's a lot of fun in this proof. We get into the business of whether models have transfer matrices or not, which is also a very cute thing. So the proof of symmetry breaking, this is the proof of, let's call it star, this thing right here, this theorem. Let's call it the proof of theorem. What I'm going to do is to kind of say, okay, we would know the theorem if we knew something else, and I'll reduce it through a succession of stages. So here are two things that one would like to use. And the first is completely obvious. If I take...
A question.
Yeah.
So what is actually the different, the formal definition of symmetry breaking? Can you just say it's non-ergodicity?
No, yes. Well, I think it's the definition of a phase transition is when there is more than one ergodic infinite volume limit. And as I said, it has this interpretation in these models, what is going on there. So symmetry breaking is one simple way to understand why the infinite volume limit might not be ergodic. Usually, if you look in the physics text, the definition of symmetry breaking would be that the field phi of x, whose mean should be 0, is not 0. As an order parameter. But to say it that way, you have to have selected in some way a direction to get rid of this part of the infinite volume limit measure. So you have to have a boundary condition to say it that way, or something. Or turn on a magnetic field, right? Exactly. So that's a good way to do it, is to turn on a magnetic field, add in an extra term here, e to the h phi, which tells the model what direction it would like, and then take the limit as h goes to 0. And that selects one of these ergodic components in this decomposition that I was talking about, wherever it is here. So the first thing is, and you can answer this for me, is what will happen if I take the expectation of phi x dot phi x? What will I get in these models? Well, phi x dot phi x is what in these models?
Beta.
It's just beta, right? Because that's especially if when I say in these models, actually I really mean in these examples rather than so. Everything I'm saying works for models of this kind, provided rho decays sufficiently as the norm of phi gets large. But keep your mind fixed actually just on the examples here, where we have surface measure. And so I'll just say that I'm doing it for the examples. And this is then beta, because the spin, this is the radius of the field phi, and it's forced to be on a sphere. Now let's look at something else, which is, that's easy. So I'll put a tick there, we proved that. Now, infrared bound, this is a bit trickier. This is the heart and soul. Infrared bound. For f perpendicular to constants. And what is f? F is just a function from lambda into the vectors, into Rn. The following is true. If we look at what we're doing is we're looking at the component of phi in the direction f. And then, I'm sorry. Actually, I have to make it complex. Sorry about this. For f complex valued, then just ignore the complex valued and take it Rn valued for the moment in your own minds, because that's actually enough to deduce this anyway. Phi f conjugate is always bounded by f inverse of the Laplacian in lambda in a product f. And I guess we need a conjugate on here in this formulation. So let me let you stare at that for a second, because it has a very simple interpretation. Think about the following thing. What would we get if we evaluated this, as we called it, two-point function? So this is just one component of phi. It's phi in the direction of, well, it's not really f. It's not really one component, because the f can vary from place to place. That's an interesting thing about this. But anyway, it's something like a phi-phi correlation. And when you compute a phi-phi correlation, there's one case where we can compute it exactly, and that's when d rho is just d phi. If this was not surface measure, but just simply d phi x, I'm going to cross this out in a second, then this would be Gaussian, right? And if it were Gaussian, you would get the inverse of the Laplacian as the covariance, and this is what you get. So this is the Gaussian this is a bound that says that the Gaussian model dominates the vector model. Now, I need my eraser. If we know these two steps, then we can prove this this theorem here, and I'll do that right for you now. So let me come over here to do it. It's a cute proof. So let f sub k be a plane wave, just like Tom Spencer was talking about, square root of modulus of lambda e to the I kx. But the k should be, as we say, in the dual lattice. We're doing the Fourier transform for functions on the lattice. And the purpose of taking the k in the dual lattice is that then the different values of k make this an orthonormal set. So fk is orthonormal set in little L2 of lambda. It's little L2 of lambda with values in Cn, I guess. It's an orthonormal set. Now,
There's something trivial missing, namely that these things should be vector valued.
they should be vector valued. Yes, I should put, yes, actually that may be even a fault of my proof.
Probably it's not important.
Yes, just a second. I think I can take them all to be, I'm sorry about that. This is a slight fault. I've left out that vector valued part, but I think I can just take them all to be the same direction. So let's do that for the moment. So let's put a constant vector here. Just constant unit vector here for the moment. We will see if that's a problem or not. I think it was not. Now, maybe I actually have to have an orthonormal basis in this direction as well. Let's look. So take that, and then we'll start by computing. We'll start with the first step here. Beta is equal to this thing. But we'll write that in a slightly different way. We'll write it as 1 over lambda sum x in lambda of phi x dot phi x. So any one of these, because it's translation invariant, for any x you put here, you always get beta by step 1. And if I put this in front, all I'm really doing is summing the same thing lambda times and dividing by lambda. Now, insert this. So actually, I think I need another. I need another index here, j, like that.
You want a resolution of...
I want a resolution of the identity. So insert this fk in the middle here. So 1 upon lambda. Sum x in lambda, just leave that lying around, and put a resolution of the identity in the middle. So we're looking at the expectation of phi x inner product fx, and then phi x inner product fx conjugate, like that. And no, wait a second, k. K in the dual lattice, so k. K. Sorry, k. And I guess I also have to sum over this j as well there. And still, no,
That's
no.
in the product.
That's now, this part is in the inner product, but so that part has gone into there, but the one upon that is still there. Yes?
Have you applied the perpendicularity to the constant or
Not yet. No, I haven't applied that to that. Well, that's very important. And one reason, by the way, well, it doesn't look like you need it, because here you could interpret this as infinity if you took f to be a constant. But let's keep that f perpendicular to constants just to avoid strange things. Now, separate out here the term where f is 0, where k is 0. So break it up into the k equals 0 part and the k is not 0 part. Let's look at the k equals 0 part. Well, if you put k equals 0 in here, you just get the constant vector 1 over root lambda times this thing, right? So, and then there'll be two of these f0s, so there'll be two root lambdas, and there's already a lambda out front. So actually what you're going to get is the expectation of 1 upon lambda, let me write it out here, of some x in lambda of phi x dotted with itself. So I'll write that as squared. That square means dot product. This is the k equals 0 term. And this is the k not 0 term. The rest of them, I have to write those out in a moment. So it's important that you understand why this term emerges, because you see this is what we're trying to prove is not bounded below. This is the variance. It's the variance because it's the square of this object here. It's the expectation of the square of that object, and I don't have to subtract off the expectation of the object itself, which is normally part of the variance, because the expectation of this is 0 by symmetry. So this is the variance that we're trying to estimate right there. So we can estimate it and show that it's not 0 if we have the power to take beta large in the theorem, and we just have to show that the contribution of all the k not 0 is small, uniformly in a way that doesn't depend on beta and doesn't depend on lambda. So let's look at the k not 0 terms. Whoops, can't do that. And that's where the infrared bound comes in. And your question, by the way, about having used k not equal to 0, or rather f perpendicular to constants, plays a role right now, because you see, if we take k not 0, then these guys are perpendicular to the constants, because the constants is the k equals 0 part. So we can use the infrared bound on these secondary terms, which are like this. Sum k not 0 and then there's 1 over lambda, which is this 1 upon lambda that was always there. And there is the expectation of phi with fk and phi with f bar k. And to that, I use this bound here. So I take f to be fk in this bound. And I get the sum over k not 0 of fk 1 over inverse Laplacian lambda fk bar by that bound. So if we call this is k not 0 is bounded by this. It's the same sentence continuing. So let's write out what that is in the Fourier transform. So it's, well, this is actually a kind of Riemann sum, right? 1 over lambda. This is exactly what you want to normalize that sum into a Riemann sum. So it's very nearly equal, when lambda is large, to the integral dk over 2 pi up to dk sub d over 2 pi of 1 over 2 sum 1 minus cosine kj. Now what have I done here? You see, yes?
I'm just getting confused what we're proving right now. I thought we were proving point 2, but now it seems we're using.
No, we're not we're using point 2. Okay, this is a proof using point 2. Thank you. Proof of theorem. Sorry, yeah. Proof of theorem using 2. Okay, that's what I meant by saying I'm going to go through a series of reductions. So we already have this. We have to prove that later. And if we have that, then we can go through this argument, because as you've noticed, I've just been doing resolution of identity and nothing else so far. And I've shown you that beta is equal to something that I want to estimate plus something else, and I'm going to use step 2, which we haven't yet got, to argue that this something else, the k not 0, is small. And if it's small, uniformly in beta it's small, then by just taking beta large, I force that to be not 0. I force this variance not to be 0. Take that large, keep that bounded as you take that large. This must be large. That's the argument. And what have I done here? These are eigenfunctions. Fk are eigenfunctions for the Laplacian, as Tom pointed out. That's their eigenvalue there. That is their eigenvalue under the action of the Laplacian. So the inverse of the Laplacian is 1 over the eigenvalues. And I have replaced this Riemann sum by an integral, which is an approximation. But this, as we've noticed, that was really the point of going through the flop, or one of the points of going through the floppy bed spring case. This is exactly the same integral, which is finite if d is bigger than or equal to 3. Yes?
We get the factor of n from the n components of the
Yes, there will be a factor. I have been sloppy about the components of f sub k. I'm going to have to leave you to figure that out because I left it out of my proof, but there is a factor of n, yes.
It will not change the essence.
It will not change the essence of the proof, but thank you. That's absolutely right. So that's the essence. Okay, just to repeat it once again, we're proving that the variance of this object, this random variable, is bounded below by using these 2 steps. This one is obviously true. This one is certainly not obvious, but we're assuming it. And if we assume it, it enables us to get a bound on the k non-zero terms here by something that remains, this is uniform in lambda and beta. So that's why we're going to get a lower bound, which is uniform in lambda as claimed. And it's going to be by something, it's basically going to show that this expectation right here, 1 upon lambda, sum phi x, x in lambda squared, is greater than plus something like, which is order of beta. And so we make it as large as we like. So if you're willing to buy what I've got so far, you are now agreeing that we just have to prove this infrared bound.
Here you have an infinity. Beta is large. Still, I don't get a small quantity get.
Right, where are we? We have where do I have an infinity?
Less than infinity.
Less than,
But
this
you
is,
wanted to prove that it's very small.
no.
Small.
No. I only want to prove that this term here does not get large as beta gets large, and it does not get large as lambda gets large. That's what I want to prove, only that. I want a uniform bound on it, regardless of what beta and lambda are. So what did I do? I used this step 2, and I got this integral as an upper bound. And you see, if you look at this integral, that there's no mention of lambda and there's no mention of beta in it. So it's a uniform upper bound, regardless of lambda and beta, right?
Just a number.
It's just a number.
In
And
1 and 2D, it diverges. The whole argument does not
Yeah.
go through.
That's right. So what happens now is that I now say, okay, I take this term onto the other side of my equation, and I see that I have bounded this thing that I really want to get my hands on. I've bounded it below by something that's order of beta, and take beta large, and you've got it bounded below by any large number you want. In particular, it shows it's not a random variable, right? Because it's always fluctuating. That's what we wanted to prove. Right, now, let's see, what can I rub out? Let's put this up and keep using this blackboard so I'm a bit more efficient. So to do step 2, so to prove 2, which is the infrared bound, I'm going to say IR bound, infrared bound. Why is it called the infrared bound, by the way? Well, when you put this f equal to that plane wave, like we did just now, it basically says that this thing is less than something like 1 upon k squared, because this thing here, you remember that I'm always saying what matters is how it behaves when k is near 0. And it looks like 1 upon k squared, just like 1 over the continuum Laplacian. Continuum Laplacian Fourier transform is k squared. It looks just like the continuum Laplacian Fourier transform at large for small k. And it's called an infrared bound because we're only interested in using it when k is near 0. And k equals near 0 is infrared. Small wave, long wavelengths. Now, I'd like to prove it, and so we use the following proposition, which is almost obvious, but is in fact incredibly hard. Let H be a map from lambda into Rn, and let Z as a function of H be given by this formula, product d rho phi of x minus h sub x e to the grad phi 1/2, like that. So Z of H has exactly the same formula as my model does. See, there's my model right up there where I can't reach it. It's a product of d rows, and here we have a product of d rows. It's just that each row, instead of being centered on the origin, is now being centered on a translate of the origin, h sub x. So you are wobbling the spheres. We have a lattice. I'll just draw a one-dimensional lattice. And you have a sphere about each point. But you're wobbling the center of the spheres when you do that, right? And so you would think that that would force the partition function to be larger than it would be if they were all at the same level, right? And that's true. ZH then ZH is smaller than, I write it as Z0, meaning put the H as equal to 0, and Z0 is just Z, partition function. If the spheres are not all centered at the same place, then there's some kind of frustration introduced by moving them, in the spins. The spins can't quite align themselves the way they'd like to. That's the idea here. And I would like you to remember, because it'll come up in the proof, that Z of a constant H is also the same as Z of 0. This is a side remark. You see, if all of these H's are constant, I'll let you figure it out. What can I do to get rid of them and make them all 0? Translation, right? So we're coming back to that same symmetry, which is so important. This thing is invariant under phi goes to phi plus a constant translation. So you can change if all of those hx's are equal to are the same for every x, I can make a global translation of phi and get rid of this thing from here, and it won't even show up there because the grad phi will kill the constant, and that's why I can see that a constant h is the same as a 0. So there's that translation invariance of the massless Gaussian coming back into play in this argument. Now we have to prove this, and I figure I'm getting questions, so I can go on, right?
Yes.
Yes. Okay. So let me see, what can we rub out? I'll rub this part out.
My feeling is we should take all the time necessary to go through the argument. If you run out of time, I would suggest, assuming that the audience sees that the same way, that you could even have an extra 15 minutes or 30 minutes in the afternoon to finish. So.
No, I won't need it. I'll be able to get through to the argument. There are a few things that I was going to throw out as bylines afterwards, which I probably won't get to do, but we'll see. It's going along okay. Now, if we know this, so again, we're going to assume the proposition for the time being. Assume proposition. So each time I'm doing this, you see I'm trying to reduce the proof to something else, and hopefully it ends, hopefully the sequence of things that we reduce it to comes to an end at some point. So assume this proposition for a moment, and then I want to prove this. So let's call this thing star. We'll prove star. This is interesting.
No, we've already proved star. We want to prove the
oh, sorry, not star. We want to prove, what do we want to prove?
infrared bound.
The infrared bound. Prove the infrared bound. Thank you. Prove the IR bound. Very good. Okay. So we want to prove this. IR bound. Well, let's prove something else first. So, 1. Let's prove the expectation. Let's take the Laplace transform of the measure, e to the minus phi f. And let's prove that that is also Gaussian dominated, namely e to the 1/2 f 1 over minus Laplacian f. So this is a claim. Now, what is it saying? It's again at Gaussian bound, because go back to this remark I had before. If in that definition of the model up there we have the product of the d rows, if the d row was Lebesgue measure, just d phi, then that's what we would get when we evaluate, because the Laplace transform of the Gaussian measure is a Gaussian. We've seen this formula many times. So that's what we would get. So it's really a Gaussian bounding still. Okay, so now how would you prove this? How would you prove that you get this if it really was a Gaussian model? What would you do? You'd complete the square, right? So, so this is the proof. We have 1 upon z, and we have product d rho phi x, x in lambda, and we have e to the minus 1/2 grad phi. I'm writing out the left-hand side, and we have e to the minus phi inner product f. I'm actually making this claim for f real. So f, have I said that already? For f lambda into the Rn. Admittedly, the statement that I wanted here had some complex f's in it. But if you knew this statement for real f's, you would know it for complex f's, because you could write each f as u plus iv, and you would find it. So it's enough to do it for real.
You only consider real fields and you never use complexity over there.
Well, I did, because I used e to the ikx somewhere. My f of k was a plane wave, a complex plane wave. You could, yes, exactly. I could have done cosine and sine, but I hate cosine and sine, and I love e to the ikx. So you've got e to the ikx instead. So, so here we go. we want to evaluate this integral, and the only obstacle in our way is this pesky d rho, which is not Lebesgue measure. Because if it was Lebesgue measure, what would I do? I would change variables to complete the square up here. So I would write phi tilde is equal to phi plus h, and I would choose h to be the inverse Laplacian. This is always, in case I forget to say it, it's always the inverse Laplacian with periodic boundary conditions on lambda acting on f. That would be my translation. If I make that change of variables in here, that linear term will be part of a completed square thing. And what I will get is 1 upon z product d rho phi x minus hx. So x and lambda. So, Gaston, I think I've got the right sign now. Grad phi, this goes away, and in exchange for completing the square, you get this factor e to the 1/2 f 1 over minus Laplacian f, like that.
Here it's important that f is orthogonal to the constants.
Yes, yes, exactly. Here it is, because I couldn't have found my h otherwise. Yeah, should I say that? F orthogonal to constants. Good, Marat. So that's what you get. So in other words, I evaluated this integral pretending it was Gaussian, but the price I had to pay was that the translation that I did ends up in the d rho. That's because it isn't Gaussian. But this is a very common tactic. Pretend things are Gaussian and evaluate them as if they were and hope that that is going to be good anyway. And it is going to be good because this 1 upon z, this thing here is what I call z sub h, z of h, right? Or maybe it's z of minus h. Z of h defined here. So we know that that's less than 1. So we get this Gaussian bound, e to the 1/2 f 1 over minus Laplacian f by proposition. Now that's the proof of the claim. It's the proof of the claim. But then from the claim, we can rapidly deduce this thing. Basically, it's the double derivative. Now, normally, if a is less than b, the double derivative of a is not going to be less than the double derivative of b. Probably most of us have made that mistake somewhere, sooner or later. You can't differentiate inequalities, but you can, in fact, differentiate this one. It's kind of strange. So let's just quickly see that. So to get the IR bound, the infrared bound from this, replace f by alpha f in the inequality. So you get e to the minus phi with an alpha in front, f. And on this side, and there's an expectation. And that is going to be less than e to the 1/2 alpha squared f 1 over inverse Laplacian f. On this side, just put alpha f instead of f in the bound. Then subtract 1 from both sides. All these operations preserve the inequality. Still fair. Then divide by alpha squared. See, I am differentiating both sides of the inequality. I'm just trying to be careful not to lose an inequality while I'm doing it. And then take alpha to 0. Now, the reason why this might not work is because when you look at this thing here, there's a term which is linear in alpha, right? Alpha phi f. And that would be being divided by alpha squared, and so that looks like it's going to blow up as alpha goes to 0. But you're fine, because the expectation of phi in this symmetric situation is 0. So that term, which would be annoying, drops out. And so the next term in the power series expansion is alpha squared phi f, which is exactly what we want here. over here. It's that thing when f is real. The next term in the expansion gets cancelled by the alpha squared. The alpha in front gets cancelled. And if you do the same thing over here as alpha goes to 0, you'll clearly pick out this term. So I hope you can see it. This gives the result. This gives the bound, the IR bound. So that's easy. So now we come to what I said looks so obvious, this thing. This may be true for many models, that inequality. Not just the special ones that I'm talking about today. And if it were true for many models, you could prove an incredible number of exciting things. But we don't know how to prove it, except in very special class of models, which is like the ones I have today. Basically, we can prove it whenever the model has a transfer matrix, if you're in theoretical physics and if you know what that means. And if you don't, just don't worry about it. I have 7 minutes here, so I just have to think about how I'm going to shortcut the remaining few pages here.
Well, how about taking 15 minutes or half an hour in the afternoon? We have between 4 and 6:15.
That's fine with me. If anybody wants to show up and
we have a research
right.
seminar taking 45 minutes. So we could easily give you 15 or 30 minutes, as far as I'm concerned. The audience might have a different opinion.
Let's do it this way so we're not forcing them into it. I'm going to finish off actually quite a bit of the proof now. I'll show you the main idea, and if that's enough, don't come later today. And if it isn't enough, come back and I'll be here. So here is, it's called reflection positivity, the property we need. And sometimes it's called Osterwalder-Schrader positivity. Osterwalder-Schrader, or reflection positivity. Now this is the property that you need if you want these statistical mechanical models to have what's called a Feynman-Katz formula, to be connected with in some way. The scaling limits of these models are usually said to be quantum field theories. But quantum field theories, they're Euclidean quantum field theories. Euclidean quantum field theories have a connection with real quantum field theories where there's a Hamiltonian and a Hilbert space. And the significance of Osterwalder-Schrader positivity is that it shows you where the Hamiltonian and the Hilbert space is in the Euclidean statistical mechanical model, even at the lattice level. And that's why it's a very important property, but it's also one you don't always have. For example, just before I get into this, I would really like to use ZH is less than Z of 0, or a property like it, for that self-avoiding supersymmetric integral that I wrote down on the blackboard at the end of lecture 2, because then I could prove, for example, that long chain molecules have collapse transitions where they have an extended phase, and the collapse phase would be an ordered phase, and the ordered phase actually would be would correspond in this language to the breaking of a U1 symmetry. That would be a very exciting thing to do, but I can't do it because those models don't have this property that I'm talking about. So it's really, and just to put another point on this, suppose in that grad phi, I just change the model a little bit by adding some next to nearest neighbor ferromagnetic interactions. Don't have Osterwalder-Schrader positivity. I've made the model more ferromagnetic. I've made it, intuitively it wants to even more break its symmetry than it did before, but now you can't prove it. So this is really annoying that this property is very important, but we should not be using it at this point, but we are. So here's what the property is. I'm going to draw a one-dimensional model because it's easier on the lattice to draw a one-dimensional model with a periodic boundary condition, which means that the lattice sites are in a ring, right? So one end of lambda is here and the other end of lambda is there, and we have periodic boundary conditions. So we have spins at each of these points, and they're coupled by nearest neighbor grad phi interactions there. Now, in this model, I could take, there's a reflection. So you need an even number of spins here. And there's a reflection which interchanges the spins on this side with the spins on that side. So reflections, we need basically this setup. Lambda, we need a reflection, theta, which maps lambda into lambda. And then there's going to be a left half, lambda minus, and there's going to be a right half. This would be the left half here, lambda minus, and there'll be a right half, lambda plus. And theta of lambda minus is going to be lambda plus, and vice versa. So we need a reflection. And then, although I'm going to use the same letter for reflecting a function of fields. So theta of, so given f, which is a function of the fields. So I'll write it as a function of phi sub x, where x is in the left half, or maybe I want the right half. Which way around do I want it? Just a second. So let me put 1 and 2. I'll put them in the right half. Right half. That doesn't matter, but I just want to stay consistent with my notes. So my notation here simply means that f is a function of these fields here, here, and here. Those are the x's which are in the right half. F is only allowed to depend on those fields. It's not allowed to depend on these fields. Define the reflected f, theta of f, which is a function of phi x, where x is in the other side, in theta of lambda plus, by replacing phi x by phi theta of x. Just to be concrete about this, suppose that f was, let's number these fields. We could call it 1, 2, 3, 4, 5, 6. And then if f was e to the power of phi times f1 plus f2 times phi 2, so that would be a function that depends on the fields here and here, then theta of f would be e to the f1 phi. Now what does theta do to 1? Theta takes 1 to 6, so you should put phi 6 here. And f2, 2 gets mapped to 5, so you should put phi 5 there. That's how we define theta on functions. And then we say that the expectation is Osterwalder-Schrader positive, which I'm going to write as OSPOS for short. Osterwalder-Schrader positive is OSPOS if you have the following property: theta of f times f is greater than 0 for all f of this type here, depending on fields in lambda plus. Okay, I got to quit. I can't show you the rest of this proof here, but the bottom line will be that we have this ability to do reflections about any of these hyperplanes because it's translation invariant. So there's a Cauchy-Schwarz inequality. This is just, which says that theta f g is less than theta f square root theta g square root. And if I apply that over and over again using these reflections, I can make whatever function I started with. So there's a particular function I have in mind in order to do this business. I can make it a constant h. And that's the proof. And why does it have this reflection positivity? Well, I can only explain that to the theoretical physicists here. It's because these models have transfer matrices, which are positive operators. Their eigenvalues are positive.
So is the audience guessing the connection with quantum mechanics? Quantum mechanics, we have a wave function, and probabilities are, and by squaring the wave, taking the absolute value squared of the wave function. In statistical mechanics, we have no such thing. We just have a positive probability measure. So to reconstruct any kind of quantum mechanics for statistical mechanics, we have to take a square root somehow, right? Sometimes we have to factor.
Yeah.
The left and right part. So the wave function evolving through an evolution out of one infinity and the other part coming from the other infinity and putting it together. Is this the correct intuition? I mean,
yes, it is.
How theta comes to be a player in this business in the first place.
Yeah.
And then you use it here for a certain technical purpose, which is specific to
Exactly. It's purely technical, but it has this very
when
deep
Osterwalder and
significance.
Schrader write a paper about the connection, they don't try to prove infrared bound. They want to reconstruct quantum mechanics.
That's exactly right. So here you see there's an inner product here, right? I mean, you might think that the inner product to define your Hilbert space would be just F with G, but if you want to define the Hilbert space which quantum mechanics lives on, you use this inner product. You take functions which live on the right-hand side. Actually, you can take functions that can live on a single plane. That's enough too. You define an inner product on functions that live on a single plane by this kind of tactic here, and that's the Hilbert space of quantum mechanics. And that's the Hilbert space where the Hamiltonian lives and everything else.
So we first of all thank David.